Hi, this is Thomas from Pinswick Audio, and this is my new module TLBX or toolbox. Toolbox is a Swiss Army knife utility module in 2 HP that is very skiff-friendly, packs a ton of features, and can fit into almost every case. Toolbox can be a lot of things. It can be a 1 to 5 multiple, a 5-channel mixer and everything in between. It can be a 2-channel stereo mixer, a voltage reference, a precision adder, a voltage multiplier, a voltage range converter, a comparator, more, and multiple of those things at the same time. But we are getting ahead of ourselves, because at its core, Toolbox is quite simple. Toolbox consists of 3 sections. The first section is a 1 to 2 multiple. The second, a 2 to 1 mixer. And the third one is a 2 to 2 adder or subtractor. The module is built to handle both audio signals and precise CV signals. This means you can use this, for example, as a mixer and as a precision adder without introducing errors into the signal. But what really opens up the opportunities and makes Toolbox unique is the way that the sections interact with each other. There's tons of normalization going on, which turns the module into much more than just the pure sum of its parts. Let's put Toolbox into a case and see it in action. There are multiple levels of complexity to Toolbox. All the sections are not only capable of working on their own, but they are normalized to each other. And they are normalized from the top down, which means that the MULT section will influence the mix section and the DIFF section, and the mix section will influence the DIFF section. How does that look like? Let's start with level 1, which is multiples and mixing. As we already seen, we can use the first section as a 1 to 2 multiple. So if we connect something to the first input and cables to the following outputs, then we have 2 copies of that signal. Just a standard 1 to 2 multiple. But what if we need more than 2 outputs? We can do just that by just going to the next output and using that one. And as you can see, it is also a copy of the previous signal. That is because from the top to the bottom, all the inputs of a section are normalized to the previous one, which means that whenever you have nothing plugged in to a section, then the output will be a copy of the previous one. The normalization works on a per section basis, which means that whenever you plug a cable into any input of a section, the normalization will break. So either this one or this one will break the normalization. And the same principle not only works for the mix section, but also for the diff one. So if we needed a 4th output, we can just connect it here. And because we have nothing connected to the inputs of the diff section, a copy of the previous section, which is the mix section, will appear here, and we can see it here. And this will also hold true for the 5th output, which means like this, we have a 1 to up to 5 multiple. If we go from the top to the bottom and connect just outputs in a row, then we will get multiples of the previous outputs. How does it look like for mixing? For mixing, we go instead of top down, from the bottom up. Let's start with using the mix to mix 2 waveforms here that I've prepared. And as you can see, this is 2 waveforms summed up. But what if we wanted to add a 3rd waveform into the mix here? We can do that by just going up from the section that we just used to the previous one and connecting something to the input. And as we can see, another waveform is summed on top. This works because not only the inputs are normalized, but also the outputs of a section are normalized. If we plug nothing into the outputs here, the signal will appear in the next section or even in the next sections. Just like that, we have a 3 to 1 mixer. If we want to do the same as a 5 to 1 mixer, we can also do that. Let's do the same game upwards. So this is a 3-channel mixer because we've plugged nothing into the output and something into the input. This is a 4-channel mixer and we have one input left this is a 5-channel mixer. Whenever we plug nothing into the outputs, we can mix the signal together into the output that we're using afterwards. Let's go one layer deeper, which is stereo mixing, because here we have multiple signal paths. The basic stereo mixer is pretty straightforward because we have a 2-to-1 mixer and a 2-to-2 adder subtractor, and we can use both of them as a 2-to-1 mixer. So if we take one output here and add something to it and show that on one of the channels, and we do the same for the other channel, then we have 2 different signals, one for both sides, which are mixed completely independently. Now it gets really interesting if we want to add something else into the mix, because we still have an input left. What we can do now is we can use that input to sum a mono signal into both channels to make it a 2.5 channel stereo mixer. So if we go from here into here, the signal will appear on both channels and will be summed to both. This works because not only is there straightforward normalization from one section to the next one, but for the MULT section, there's a split of the signals. One of the signals will go to the mix section, and the next signal will go to the DIFF section. So here we have 2 copies of the signal, one goes here and one goes here. So we have a 2.5 channel mixer, which is pretty useful. Let's go to the next level, which is voltage references and transposition. The whole module is built to not only handle audio, but it can also handle pitch CV all the way through. So everything in here is made to be very precise, and every mixer can be used as a precision adder, and every multiple is a precision multiple. As we said earlier, we have all the sections normalized to something, and the MULT section is at the top, so there's no section come before that. Because of that, there's an alternate function in it. If you connect nothing to the MULT section, then on the outputs here, a reference signal will appear. The first one will be a 1 volt reference, and the second one a 5 volt reference. And because the whole module is precise, these are precise as well. Especially the 1 volt output is calibrated so that it's accurate to less than 1 millivolt of error. So you could even use this as a reference to calibrate an oscillator, for example. But for the most part, we can use this to transpose something by an octave up or down. Now, one thing you might wonder is, why does the output here not appear on the signals below? Because if we plug something into here and here, it is just straight 0. This is because there's some advanced logic going on here. So if you plug nothing into the input here, then the outputs will show the reference signal, but the reference signal will not be normaled to the next sections. So you don't have to worry about always plugging something into here. You can safely ignore it. It's basically just an extra and does not change the functionality of the rest. Now, we can use this voltage reference to easily transpose something. So we can use this LFO again, and we want to transpose this LFO by 1 octave down or up. We can do that easily because we have the reference here, and we just connect the reference to the second input of the adder subtractor, and both outputs will be transposed now. One will be transposed 1 octave up, and the other will be transposed 1 octave down. Let's go another level deeper, which is voltage multiplication. The normalization can not only be used to just mix signals in a unity gain, but it can also add up signals multiple times. So it can be used as the voltage multiplier. This is especially useful with references. If we want a 2 volt signal, for example, we can do that. And if we take a closer look at the mix, we can see in the mix section that the both inputs are not only connected to the MULT section, but the second input is normalized to the first one, which means that if we plug something into the first input, it will be doubled on the output. If we connect the 1 volt signal, the 1 volt reference here, and connect this to the output, we have 2 volts on the output. If we break this connection, it goes down to 1 again. This is the simplest way of multiplication, But there's even more that we can do. This will double the signal. But what happens if we plug this in here and nothing in here? We have the signal 4 times. This is because now we don't have anything connected on the output here, and we have nothing connected on the inputs here. The signal already doubled here, so it goes from 1 to 2 volt, and then it gets summed up twice here from 2 volts, it gets to 4 volts. The same principle not only applies to internal signals, but to externals as well. And just like that, we have a pretty precise voltage multiplier. So if I were, for example, to plug this into an external signal, like the same 1 volt reference here, we obviously get the same result. But really, it gets interesting if we connect it here, because like this, we have a 3 times multiplication. And if we sum the signal another time, we get a 4 times multiplication. And if we even plug it in here, we get a 6 times multiplication. Like this, you can get a lot of different, pretty precise multiplications if you ever were to need this. Let's put all that we've learned to test and go another level deeper. Now we know how to create a voltage reference, how to multiply it, how to add an offset, how to mix and multiply. One scenario where this actually comes useful is voltage range conversion. Say that you have a signal which is of a specific range, for example, -5 to 5 volts. Sometimes we want to convert this to another range. In this case, this would be a bipolar signal, and we might want this as a unipolar signal of a range of 0 to 5 volts. And with toolbox, we have all the tools at our hands that we need to do this. So the first thing that we need to do is transpose the signal up. Instead of -5 to 5 volts, we need the unipolar signal of 0 to 10 volts. So we take the output, put it in here, and we add 5 volts. And if we take a look at the signal, we can see that it's already unipolar. Don't worry about the signal being cut off. This is just a limitation of optics because it cannot display any signal that goes close to 10 volts. Now that we have the signal from 0 to 10, how can we halve this? Because we have not yet found a way to do this. This is the last ace up of toolbox sleeve, and this is the little triangle showing down below here. If you plug nothing into the output of the mix section, then a copy of the signal will appear here, which is exactly half of the signal before. If we terminate the inputs of this section and put this here, we can already see that what we tried to do worked. Instead of -5 to 5 volts, the signal will now go from 0 to 5. We shifted upwards and we halved the signal range. Because of this possibility to divide the signal by 2, we can actually do a lot more signal range conversion. You can convert everything in between the ranges of -5 to 5, 0 to 5, or 0 to 10. One more example for voltage range conversion is going the exact other way around. So we have a signal which goes from 0 to 5 volts, and we want to convert it into a signal which goes from -5 to 5. The first thing that we need to do is we need to copy the signal and multiply it by 2. Then we already have a signal which goes from 0 to 10 volts. And now we just need to shift this downwards. And we can easily do that by using the next section and also using the 5 volt reference and subtracting it from the previous signal. So just like this, we have the conversion into the opposite direction. 0 to 5 volts to -5 to 5. There's one last level left, which is feedback shenanigans, for example, comparators. Up until now, we just connected from the top to the bottom, so always into one direction. And that is, in 90% of cases, the way that you should do things. However, you can patch feedback patches here. All the components are made, so this is nothing that will break anything. Most of the time, it will lead to very spectacular results, but sometimes it can actually be useful. Say we need a comparator. How can we do that? In this case, we can do this by just feeding back the output of the mixer back into itself. So basically now it can only have two states. Either it's full positive or full negative. And now we can influence the signal by putting something else into the input. And obviously now we can see something, but now we can apply what we learned earlier about the outputs. We can use the bottom output and actually grab the signal that we've now created. And we have a comparator signal. Whenever this signal goes above 0 volts, it will go full positive. And if it goes below 0 volts, it will go full negative. There's one more feedback patch I want to show you, and that one has to do with the diff section. The mix section only has positive feedback, and positive feedback will always lead to something like the comparator, which will always hang at either maximum positive or maximum negative. But here we have a negative output, which allows us to do actually negative feedback. And that gives some really interesting results. If we use the negative output of the diff section and put it back into the negative input, and then take the 1 volt signal as a base and look at what comes out, then we can see that we just built a voltage multiplier that gives us 1.5 times multiplication. This is one more puzzle piece, what you can do with it in terms of voltage multiplication or maths. We can actually achieve almost every voltage between 1 and 10 volts as a reference, and minus 10 and minus 1 volts as a reference, and even some very useful voltages like 1.25 volts and 1.5 or 2.5 volts, which we can use maybe for calibration of other modules. So this was Toolbox, a very small module which packs a lot of functionality and can go really deep while only taking up 2 HP and fitting in almost every case. I hope you find the module interesting and intriguing. I hope you enjoyed the video, and thank you for watching. Bye.